I'm going to speak today about plastic semiconductor materials and their application in photovoltaic energy conversion. So as Marco has said in his introduction, I've been working on photovoltaic energy conversion for a very long time, possibly since before some of you were born. And there's a good reason for that, and that is that if we look at the abundance of the different energy sources available to man, solar energy represents a resource which is abundant in the extreme above what is required. So, for example, if we consider the availability of radiant power density on the surface of the Earth, it varies a bit from place to place, but typically we're looking at a couple of 100 watts per square meter in terms of the energy resource. And that is a resource that greatly outweighs consumption, even in countries where you have relatively little solar resource and a relatively high consumption, relatively high population density, such as the UK. So, for example, in the UK, where each individual has a share of, let's say, some 500 kilowatts in terms of the solar resource, that's still 100 times greater than their primary energy consumption. Of course, there are issues to do with conversion, how much of that energy can we actually extract, but there's no doubt about it that solar energy is a very significant resource and one that we have to pay attention to. So that confidence is shared by bodies such as the International Energy Agency, and in their projections for power sources out to 2050, it's projected that some 11% of electricity will come from photovoltaics by 2050, and if we also include concentrated solar thermal energy conversion, the fraction rises to about a quarter. So we're really depending on solar power to deliver. So where I'd like to start is with a view at how it works. What is photovoltaic conversion? So the job that we have is to take the energy that resides in photons that arrive from the sun and convert that into electrical work. And the fact is that the sun provides us with photons in a range of different energies across the visible out into the infrared. And what happens in photovoltaic energy conversion is that photons of energy greater than a certain energy gap are absorbed in a material, and when they do that, they promote an electron from a ground state to a higher state, and that then generates some electrochemical potential energy. And if we can capture the electrochemical potential energy and extract those electrons into an external circuit, and then drive them through some resistive load, we can get the electrons to do electrical work, and we have effectively a conversion from the radiant power in the sun into electrical work. That's what we want to do. And what we need to do that, at a very basic level, there are really three things that we need. We need a material that can absorb photons from the sun. We need a means to keep those the electrons that are excited to higher energies at a higher energy for long enough to be collected, and that's achieved using an energy gap. And then we need some asymmetric contacts between this light-absorbing material and your external circuit. And so if you have light absorption, an energy gap, and asymmetric contacts, then you have the means that you need to generate a photocurrent and to do photovoltaic energy conversion. So at a cartoon level, we have something like this, where we have photon is absorbed, promotes an electron, delivers, the electron is collected, and goes through the external circuit. Now, the key thing here is how do we achieve these asymmetric contacts to the external circuit? And that's done traditionally using in a PN junction solar cell, such as a silicon solar cell, by having a layer of material which has a different composition on the front compared to the back. That's done by introducing impurities, different types of impurities, into the front cell and the back of the device, and it makes the front of the cell more attractive for the promoted electrons to go to. And so you have, if you like, a sink for electrons at the front of the cell, and then whenever an electron is promoted by a photon, it will preferentially diffuse towards the front of the cell, and that gives you the direction that you need to generate a photocurrent. So if the great majority of photovoltaic technology until now has been based on crystalline silicon and polycrystalline silicon technology. So the modules that you'll see installed on buildings and elsewhere are almost always based on silicon. And this technology has been enjoying a very significant and impressive growth over the last 20 years, with a rate of growth averaging around about something like 30% per annum. And at the end of last year, the installed capacity accounted for some small fraction, about 0.2% of global electricity provision. But although it's growing fast, the installed capacity is not quite growing fast enough in order to meet the expectations from solar power. And the reason why not is effectively the large capital cost of the silicon technology, and that derives from the cost of purifying and processing silicon wafers, which are used to make solar panels. So if we want to enable photovoltaic power to be implemented more quickly and taken up more quickly, we need to find a way to reduce the cost per unit. The cost per, we talk about in units of capacity in terms of peak watts. So what we have is light energy being absorbed, electrical energy being generated, and it costs us something to build the device that does that conversion. If we want to do it more cheaply, what can we do? Well, we can really consider two alternative approaches. And one is to find a way to do the energy conversion more efficiently, so that you get more electricity per unit capacity. And the other way is to find materials which are cheaper than crystalline silicon. And indeed, I've worked on both approaches. In terms of the first approach, I mean, for example, there are other materials. There are multi-layered materials that can be built into multi-junction cells that have higher efficiencies. And they can be made to work. They do work well, but the problem is that you're increasing the cost, the capital cost of the devices quite significantly. And the alternative route is to look at materials which are themselves cheaper, and they might not convert light into electricity as efficiently as silicon, but when everything's worked out, they could do that more cheaply. And so this really is where plastic electronic materials come in as a candidate for this route. So we're speaking here about materials which have the property that they're based on molecules. They have the very attractive properties, first of all, that the specific properties, so that means the color, the electronic properties, and the structural properties are largely controlled by the properties of the molecules which are used to make the thin films. And from the point of view of a technology development, apart from this sort of tunability of the properties of the materials, they have the advantage that in many cases the materials can be processed through some large volume manufacturing techniques such as printing, coating, but other also varieties of solid state processing. So we have, as I've said, the solids where the properties are dominated largely by the properties of the molecules which are assembled together into the solid films. And the electronic properties of our solids are controlled largely by the molecular structure. So just as a cartoon here, I take the example of a very simple example of a plastic electronic material. It happens to be anthracene. But the molecule has a property that the carbon atoms, so the molecules are based on a backbone of carbon atoms, which are all in the what we call the sp2 hybridized state. And in the sp2 hybridized state, it means that there is attached to the carbon atom one electron which is more loosely bound than all the others. And when we bring together these carbon atoms into a network, these more loosely bound electrons form a set of levels where they are relatively easily excited by visible light, and where they can relatively easily move from one atom to another. So you have a network of these carbon atoms. It tends to be a flat network. And if we can understand how the electronic properties of the molecule depend upon the structure, then we can design materials, and we can design materials that have certain response to visible light, and we can, in principle, design materials that have certain electronic properties. So there is this great capacity, if you understand the materials, to design new types of materials that have particular properties, and that has really been exploited in developing materials for solar cells. We'll come to that later. So apart from having this tunability, the materials are effectively soft solids. And as a result of that, they have the capability to be prepared in a number of different states. You may have crystalline or amorphous films with different mechanical properties. And as I've mentioned before, because the basic component is a molecule, we have the potential to process the materials using techniques like solution processing, which are used for conventional plastic materials. And that means that you can think of processing thin films of your semiconductor on flexible substrates through a process which is similar to processes used to print newspapers, to produce plastic bags, or whatever, but really sort of technologies that are used for commodity products, and therefore in high volume and producing products relatively cheap. That is what is really attractive about these materials for photovoltaics. So what we would like is to have a kind of a technology where you design the materials you want, and you then solution process some layered structure, which is going to be a solar cell with different contact front and back to direct the photocurrent. Light will be absorbed inside, and current will be collected, and then you could process your sheets into different types of products. And this is and I think this was actually the first organic plastic photovoltaic product that was actually marketed. It was a courier bag marketed by Konarka Technologies about 2.5 years ago. So just now thinking about what the challenges are in making that happen. So I commented that we're dealing with molecular materials, and to give some examples, we have, I've said that the basic building block is a carbon atom which is in its sp2 hybridized state. That means that they link together into some kind of planar structure. This is an example of a pi conjugated molecule. It has a number of lobes, and each lobe you can see is a kind of flat structure that's made up from a number of carbon atoms that are all electronically connected together. This one is familiar, I'm sure, to many of you. It's C60, or Buckminster fullerene, and that is actually a very, very important ingredient in plastic photovoltaics. And then we have conjugated polymers, which are very long strings of these atoms. And the advantage of moving from molecule to a polymer is that a polymer has the material properties that allow it to be processed from solution, and that give the material some mechanical strength. So these are the types of materials. Now, the really key thing in shifting from an inorganic semiconductor like silicon to an organic semiconductor like any of these is that the type of state that's generated when one of these materials absorbs a photon of light is localized. So If we absorb a photon in a small molecule like C60 or this AlQ3, then we'll generate an excited state which is more or less the size of the molecule. If we do it in a conjugated polymer, then we'll generate an excited state which is much smaller than the size of the molecule. And we call this type of excited state an exciton, and effectively it's a combination of a positive and a negative charge. And what we want in any photovoltaic system is we want that excited state, that's a combination of positive and a negative charge, to break, so that we have a positive charge and a negative charge separated from each other, and the charges move and they give us an electric current. So we would like those states to break up easily, and that's a problem because in molecular electronic materials, because we have an assembly of molecules that's really not held together by anything very strong at all, the excited states tend to be localized on the molecules and they don't want to move. So we have to take a different approach. So I'm going to try and illustrate that in the next slide. So if, for example, we have a crystal of something like silicon, this is a cartoon of silicon, doesn't look anything like that, but let's just pretend it is. It absorbs a photon of light, and that creates this state where you have an electron and a hole, and they're in some kind of orbit around each other because they're attracted to each other. But they're not very well attracted to each other, and that orbit is rather big. And you can break them up with an energy which is really quite small, so around about 1/100th of an electron volt. That kind of energy is easily available at room temperature. So as soon as you absorb a photon, you have a charge pair. In our material, rather than having this sort of extended sort of crystalline state, we have a load of molecules. And when a photon is absorbed, it's absorbed on just one of those molecules. And that means that the electron-hole pair that it generates is localized just on that one molecule. And there's not very much of a encouragement for either of the charges to move to another molecule. So you give it enough time, the charges will just go back to each other and give us nothing in terms of current. So in terms of the cost of separating the charges, we need some much larger value of energy, say tenths of electron volts, to break those charges away from each other. And at room temperature, that kind of energy is not easily available. So if you take the approach that you take in something like silicon, where you have a layer of silicon and optically it's thick, you want it to absorb and harvest as much of the light as possible, you can absorb light anywhere in that structure, and wherever you absorb the light, you generate a pair, electron-hole pair, they split up, and then, as I commented before, the electrons will be encouraged to drift towards the front because its composition attracts electrons, and the holes will go elsewhere. If we try to do the same thing in our molecular semiconductor and make something that's optically thick, we have the situation where almost anywhere that the photon is absorbed, you create these pairs and they recombine. There's no encouragement for them to split, except in layers that are right next to these interfaces which are collecting the charges, and that's because the interfaces generate an energy advantage to the charges to separate. So we can't use that approach to get photovoltaic energy conversion. We have to use a different approach. And the solution that was found, and the solution that is used, I think, in every example of a plastic solar cell device, is to use two different materials. You have something like a conjugated polymer, which is absorbing the light, absorbing most of the light, and excited states are generated on it. And what we do is we introduce another molecule, and in almost every case, it is actually a C60 molecule or something very like it. And that C60 molecule is very attractive to electrons. So electrons tend to be transferred to the C60 molecule. It can be represented in terms of an energy advantage. And so when photons are absorbed, they very soon result in electron transfer to the C60 molecule, provided that there are enough of these C60 molecules dispersed well about enough. So then we revise the plan for the solar cell, and we have a layer which is optically thick, but rather than being made from one semiconductor, it's made from a mixture of two. And anywhere in that, you could absorb a photon, and because you have the presence of both materials together, you get a breaking up of the exciton and electron transfer to the fullerene, and then the electrons will hop from fullerene to fullerene and give you the electric current. And the basic, idea here that we are using a kind of what is really a step, a gradient in electron affinity to encourage the charges to move, is the same idea which is exploited by nature in photosynthesis, where when you absorb light in the light harvesting complex of a photosynthetic system, that the electron is then transferred by a sequence of steps to other species which have got a higher electron affinity, and that forces a spatial separation of the electron from the positive charge that it leaves behind. So this is the idea, and the way that is implemented is by making a thin film which contains both materials, and that is going to be our light harvesting medium, and then that is placed between two different electrode materials. Typically in a typical realization, you will have a transparent substrate, either glass or plastic, which is coated with some electrode, and then you have a different electrode on the top, and the electrodes have to be effectively of different work functions, much higher, one much more attractive to electrons and the other much more attractive to holes, in order to force the direction of the current. So that is the typical configuration. And then if we now just revise what's going on inside the device, we have at the first stage, photon is absorbed somewhere in the material. Then that's followed by the movement of the excited state that's been created to an interface with the other material, so to where the C60 may be located. And then we have the breaking up of the charges. The charges need to escape from each other, and then they need to transport through the material to the external circuit. And those are all the things we would like to happen. If they all happened with 100% efficiency, then we would have a very nice system. But of course, you don't always get what you want. And at every stage, there are competing processes going on, which effectively represent a loss of the energy that was absorbed by the sun. It's giving us something else, but not an electron in the external circuit. And so in terms of the science of developing this material technology, we need to understand what's going on at all of these stages. So what are the things that matter? Well, there are various properties to do with the materials that matter. We care how much light they absorb. We care about the structure, the microstructure, the way in which the two materials are combined together. Do they mix very, very well, or do they tend to segregate? What do you really want? And we also care about their energetic configuration. So how much, if we consider the polymer and then the acceptor, we need to care about how much more strongly the acceptor wants the electron than the polymer does. And we also need to consider the difference in energy between the levels where the charges eventually end up, because that's going to be the thing that determines the electrochemical potential that's available, in effect, the voltage of the cell as a battery, when you have it in open circuit. So all of these properties matter, and the science and the research challenges has really got a lot to do with figuring out in what way these different properties influence the performance of the device, and then asking the question, how can we find materials or ways of arranging materials that make the device perform better? So it's been quite an exciting time in this field. And I actually started to work on organic photovoltaics myself around about 2001 when it was first found that efficiency greater than 2%, a power conversion efficiency of greater than 2% could be achieved. And the thing that was very interesting about that was, so a device of the structure we've looked at was being studied, and it was a combination of a conjugated polymer called MDMO-PPV and a fullerene called PCBM. And those were mixed together in a solvent. They're spread in a thin film, one electrode on the bottom, another electrode on the top. You make a solar cell. And to measure the performance of a solar cell, you measure the photocurrent it generates as a function of the forward bias that's applied to the cell. And you would like it to have a large current, and you would like it to have a large voltage, and you would like that current voltage curve to be as square as it possibly could be, because at some point when the product of the current density and the voltage is a maximum, that is where you will run it to get the maximum power. So the kind of the standard device at the beginning of 2001 was something that gave you about 1%. And then the researchers, and this was work that was done by Christoph Brabeck and co-workers in Linz, they found that if they did something very, very simple, they changed the solvent in which those two molecules were dissolved, and they were able to increase the efficiency from 1% to 2.5%. And that was very encouraging. And it was interesting because it was telling us, so first of all, it was known you ought to be able to get much more current than this, given the amount of light that was absorbed. So it was known light was absorbed that wasn't delivering current. And what that experiment showed, it showed that by changing the processing of the materials, you can control the situation. And so it's sort of suggesting there really is some nice science to be done to understand how it all works. So that was more than 10 years ago. Then last year was a very exciting year, another very exciting year for organic photovoltaics, where really we're looking at a completely different order of magnitude. So last year there were a number of reports of more than 8%, 9%, reports towards the end of the year of more than 10%, and there has also been a report, I think the most recent, of something like 10.6% for a structure which is basically based on polymer with fullerene, but a double cell structure, and that comes from Yang Yang's group in UCLA. This is sort of a JV characteristic for one of the most efficient published devices. And the concept is really very, very similar to the concept over here. The difference is different materials and a better understanding of how things work. So efficiency is looking good, and there's a lot of hope that efficiencies significantly higher than 10% can be achieved. So efficiency isn't everything. There are other issues. And now one that's receiving sort of much more attention is the issue of the lifetime of the solar panel. The data on lifetimes is not actually as easily accessible as data on efficiencies, because it tends to be done more in a commercial environment, and therefore it tends to be more secret. But what we can say from what's known is that lifetimes of years under typical operating conditions have been reported using barrier materials that are not excessively specialized. And I know there's nice work going on this topic here in Milan. So with efficiency and lifetime both looking interesting, then that means it's time to start thinking about how that technology could be used. And most of the agencies that are trying to commercialize plastic solar cells are thinking about, as a first application, consumer electronics, niche markets, some small-scale power generation. But that doesn't mean that there aren't also ambitions for larger-scale power generation once the technology is established. So, for the remainder of the talk, I wanted to just give some insight into some of the different sort of research challenges and research activities that are, you know, going on not only in our group but in many groups now around the world, into trying to improve, if you like, the applicability of plastic photovoltaics. And I would like here to sort of distinguish different stages in the research activity. And part of the reason is to point out that it's a very interdisciplinary field where it requires, you know, it requires the involvement of chemists, physicists, material scientists, electronic engineers, processing engineers, people with very, very different skills. And in order to kind of make to make the idea a reality, it requires involvement all along the line. So I don't know where we start this cycle, but if we start it with the idea that we want new materials which we think will work better, we then need to understand the structural, spectroscopic and electrical properties of those materials. We would then, having used them in devices, we would like to improve the performance, increase the lifetime, and then having got a material you like, a device structure you like, think about how you could manufacture on a larger scale and think about applications. And in almost every stage, you would need some type of modeling tool to help understand how things work. So for the first example, I wanted to pick on new materials. And I'd simply just comment on here on an example which gives a view of how things have changed, how understanding has developed over the last 5 years or so. So the idea is we want this would have been kind of the best plastic solar cell in comparison with silicon as of about 5 or 6 years ago. And what was always accepted was that the optical gap of the polymer, so that determines the wavelength of light that it can absorb, will determine the current. And the way in which the energy levels of the polymer and the acceptor line up, that would determine the voltage. So if you could design materials to control their energy levels, you could then, in principle, improve performance. And if you then sort of take these principles and work them into a simple model, then you could figure out what power conversion efficiency might be available if you could change the optical gap and change the way the energies line up. And that sort of approach would suggest that you want a lower energy gap material than the one that's used here, and that there's really quite a narrow range of positions for the HOMO of the donor that are going to work. So then using that, we could then look at some different type of materials, and these are just some of, I mean, there must be hundreds of polymers that have been studied with a view to their application in photovoltaics. To absorb well into the visible, you almost always need what's called a donor-acceptor copolymer structure, where you have two different units connected in series going AB, AB, AB along the chain. And by the choice of those different units, that will control the wavelength of light that can be absorbed. But you can also, and so by changing the chemical structure of those units, you change their individual properties. But another thing which matters is how is the sort of the kind of the steric or structural property of the molecule. And if you want to have low energy gap, you would like to have a low torsional angle between the two different bits of the molecule, because that will influence the energy levels. And so a series of, for example, different polymers have been made, and this was sort of directed by partly by chemical intuition and partly by calculations of where the energy gap should be, where the HOMO should be. The calculations and experiment agreed very well. And then it was of this particular set of materials, it was found on the basis of energy levels and given the sort of contour plot, this one ought to work the best. And then in practice, of the trials, it did work the best, and then that encouraged the chemists to put more effort into making a better polymer, and it worked even better. So I simply mention this to sort of say how over the last recent years, the understanding of what you want from the materials has improved quite a lot, to the extent where there are now design tools that can help you to identify what is likely to work well, and that then saves effort and will save time in the development of new materials. So to take another example, and this of course is reasonably close to my heart because I'm a modeler by training and at heart. And where I started working on photovoltaics was in making models of how new types of devices perform. And what you would really like, and particularly if you were a synthetic chemist, what you would really like would be able to say, I give you the chemical structure, you put it into a model and give me the device performance you're going to get from it. And this is impossible. But nevertheless, it's an understandable desire. And part of the reason why it's not really possible, so if we're working with something like silicon or gallium arsenide or another semiconductor, we understand the band structure, we understand the electronic properties of the material, you can use some device modeling tool, and you can make a model of, okay, if you make your PN junction like this and you have your electrodes like that and you shine that much light on it, you ought to get a response like that. We can't do that because this stage is too difficult. We don't really know how the chemical structure is going to influence a device performance. And that is largely because our material is very disordered. It's a molecular material. It has the advantage it's easy to process. It has the disadvantage that it's disordered, and the configuration of every molecule within the solid film is going to be a little bit different. In terms of electronics, that means that you have different energy levels which can be occupied by the charge carriers. And most of the sort of semiconductor device physics doesn't really accommodate that. It doesn't accommodate having a wide range of different energy levels for the charges to occupy. And so to put it simply, we could say we can't actually do that because we don't really know the rules. But there's been some progress towards that goal, and just to take some recent work from our group, we've been developing adapting device models that can include some different energy levels for charges to occupy. And then when we put those into our device model, we find we can explain the performance of devices under different conditions. And a way in which this approach can be useful going forward is when we look at the important phenomenon of degradation of our materials. We could use this type of modeling tool to diagnose what might have gone wrong when the device performance starts to get worse, and then try to relate that to particular defect states that could be related to some chemistry going on in the device, and so solve that problem. So moving a little bit away from the sort of detailed science now, I take another issue. And this is, it's also related to device stability. And so if you remember, for this to work, we need to have two materials in our solid film. And those two materials, by and large, don't like each other very much. And if you give them enough time and enough heat, they'll separate from each other and give you donor over here, acceptor over there, no solar cell. And these are some old data from another group that show that very thing happening as a photovoltaic film is exposed to moderate heat over a period of time. And that can be understood from a materials science point of view, from knowing that the two components in here, although one is a polymer and one is a molecule, they're relatively low molecular weight components. And if we compare them with conventional plastics like polyethylene or something like that, they're very, very low molecular weight. So a possible approach to this problem would be to include in this binary blend a third component, and to use as the third component something like a commodity plastic like polyethylene or polystyrene, which are available with very high molecular weights, and their very high molecular weights would then impart a certain amount of mechanical toughness to the component film. And we tried that, and this image here shows a sort of the result of one student's Friday afternoon, I think, but he put together the two photovoltaic components and a small amount of polyethylene, and was then able to show that you could produce a film that was quite easily processed. And in spite of putting in this other component, which really, it's electrically, it's an insulator, so it should be a problem, but if you don't put in too much of it, you don't lose in terms of photocurrent generation. You might lose a bit, but the advantage of having something which is mechanically tough and therefore likely to last longer can easily outweigh the disadvantage of a lower current density. So, to almost conclude, I want to then address the question of what could these plastic photovoltaics actually do for us. And here it's worth looking at what's been happening in the development of the conventional silicon-based photovoltaic technology over the last, I think that's over the last number of decades, say 3 or 4 decades. And this data, so I borrowed this from Martin Green at University of New South Wales. And so we have here the first silicon solar cell in the early 1950s, then renewed attention to solar cells in the 1970s as a result of the oil price hikes. And then from the early 1980s and into the 90s, more attention. And you can see that the efficiency of the best silicon solar cell is increasing all this time. And eventually it plateaued around about 1990, 95. And recently there haven't been much performance at all. But if we look on the same timescale at what's been happening to the cost of silicon photovoltaics, it's continued to come down. So to begin with, it would have been coming down because efficiency was improving, but more recently, efficiency hasn't been improving, but costs are still coming down. And costs are coming down largely because of step-by-step incremental innovations in the technology that result in the manufacturing and the design of devices that are brought about because of the market for photovoltaics, because there's interest in using photovoltaics and, I suppose, in making money out of them. So if this is what's been happening with conventional solar technology, we could then ask, what might we be able to do with this trajectory if we have some new technologies available? And so for comparison, we can then look at what's been happening, and unfortunately I can't keep this graph up to date enough because we're now higher than the highest point here, but it gives the point I want to make is that over the last 10 years, the efficiency of organic photovoltaics is steadily increasing and it's still improving. So we're doing what silicon was doing in the 1980s or even in the 1950s. And if this technology was actually applied, when it reaches the point of being applied, the new materials will introduce opportunities for innovations in materials, in manufacturing, in device design, in applications, which would have the potential to further push down costs. And by further pushing down costs, then that can accelerate the deployment of photovoltaics. So sometimes people will ask the question, do you expect plastic photovoltaics to replace silicon? And my answer would be absolutely not. But what I would expect plastic photovoltaics to do would be to enlarge the range of opportunities where it makes sense, economic sense, where it is economically possible to use solar power now or in the near future, rather than sitting back and waiting for costs to come down through increase in a market which is largely dominated by silicon. So if we want to look at what organic photovoltaics can do, we're actually in the advantageous situation of dealing with a technology which is pre-commercial. So it means that you can actually look nowadays at how you imagine plastic photovoltaics being produced and how you imagine them being used, and do an analysis of what the cost is of different stages involved, but also, and importantly for the future, the energy cost of the different stages involved. And we do that with a life cycle analysis approach. And with the life cycle analysis, we can identify what are the limiting stages or materials involved. And a study that my colleague Antonio Urbina completed about a year ago concluded that indium tin oxide was a really big problem. And the conventional approach always uses indium tin oxide. But because we're not yet locked into indium tin oxide, we can look at alternatives. And so one of the things that we can do, and it's enabled, I think, by the fact it's a pre-commercial technology and the fact that we have this huge diversity of different materials that could be used, we can look at how the cost effectiveness and the energy effectiveness of our plastic photovoltaics could be improved by replacing indium tin oxide with some other materials. And so that's another way that we can kind of try to optimize the technology and plan for the future. So the final slide I wanted to show is this one, and this is the work of my PhD student, Chris Emmett. And of course, I don't expect you to be able to read anything which is in this graph here, but basically what he's done is he's asked the question, supposing I have two types of photovoltaic technology, organic and silicon, and they're both present in the market, and we look at we make a constraint that the area available to harvest solar energy is fixed. And then we look at the two configurations, one where OPV is accelerated and the other one where where OPV is growing faster and the other where it's not growing so fast. And then see what the effect is in the end on carbon emissions mitigation. So in the two cases where OPV is accelerated, then we have a growth in the area covered by photovoltaics, which is faster at the beginning because OPV is cheaper, that's the reason. And then ultimately the area saturates. And then we can look at the net effect on carbon savings. And what we see is something quite interesting, which is that up to a certain point in time, the cumulative emission savings will be higher if you prioritize OPV and allow that to grow quickly. And then in the very long term, you really want high efficiency technology. So clearly, if we're looking to the future and trying to meet emissions targets in decades hence from now, it's going to make sense to consider all of the different technologies we have at our disposal and try to find the best possible mix to minimize, to maximize emission savings and sort of accelerate the change to sustainable technology. And I will argue that something like plastic photovoltaics has, as far as we're aware, still got a place in this. So to summarize, I've argued that photovoltaic power is seen to be a key component in decarbonizing the electricity supply in the future. And OPV technology is something that has the advantage of using materials and processes which are relatively accessible and relatively low cost, and as such it could increase access to photovoltaic power. We've seen a spectacular improvement in the performance of this type of technology over the last 10 years. A number of challenges still remain, but they are, in my view, all addressable. We don't yet have any good reason to ignore this possibility, and I think I would argue that we can't really afford to ignore that opportunity, at least not yet. So I've closed by thanking you for your attention.